Okay, cool. Let's jump right in. So we're going live, and we are going live for the second time today. Hello, everyone. Very, very nice to be here. Once again, this is live stream number 79 for the Data on Kubernetes community. We're on a very, very solid streak of lots of content as we get closer to KubeCon. And this stream, I was talking to Chris before we got started. Particularly excited about this one for a couple different reasons that we're going to get into it. We have a person who's been in the space for a while, and on top of it has been approaching it very much on his own through having a company. He's going to explain a little bit about that before getting into DataStax. And what does that mean? It means lots of close contact with end users, really understanding what makes them tick, what they're willing to pay for, the kind of difficulties and frustrations that they're having, and what different technological answers can provide to that. What kind of value can be provided there. And speaking of value, lovely segue. If you would like to add some value to our KubeCon event, our co-located event that we'll be doing on October 12th, I will happily leave the CFP here in the chat so you can take a look at that. If you want to give a talk, the two criteria are you need to be speaking about working with stateful workloads on Kubernetes. That can be in a variety of different ways. If you have questions, you can ask us. And the other criteria is really bringing in the end user focus. All right, we want to make sure that it's not just vendor pitches. We really want to be thinking about how these technologies and solutions are being applied in real life circumstances. What are the use cases? What's the impact that's being generated? So that's all I got to say for now to get started. As usual, you can feel free to leave your questions in the chat. And that being said, I'd like to introduce our speaker today, who is Chris Bartholomew, who's joining us from Canada. Welcome, Chris. Very nice to have you with us.
Pleasure to be here, Bart.
Good stuff. So, Chris, can you just give a little bit of background about, how you got into this whole data space, and then maybe we can build this into, how you ended up starting your own company?
Sure. I've been working sort of in the messaging streaming space for a long time now, since mid 2000s. I worked for a company here in Ottawa, Canada, where I live, that built purpose-built hardware that did this kind of stuff for very low latency, high performance. And, over the years, new technologies come along. And one thing that I was always intrigued with sort of in the later part of the time I was working there was what Kubernetes and how we could leverage Kubernetes. And it was something that I was trying to get started at my previous job. And, there was a little bit of traction there, but I really felt that Kubernetes was going to be a key way of deploying applications and sort of become the, operating system of the enterprise. And so when I quit that job and I set up to build my own company, I decided to make a strategic bet on Kubernetes. Everything was going to be on Kubernetes, including, not just the stateless stuff, but the stateful stuff. And in particular, my idea was to build a SaaS on Apache Pulsar, which is an emerging competitor to Apache Kafka. It has a lot of the same capabilities as Kafka, and it has a lot of other really cool capabilities on top of Kafka. So when I went to approach that, I said, the first thing I'm going to do is I'm going to run Pulsar on Kubernetes. And so, there was some beginnings there, but, I had to build that out and get that working, figuring out how to get it to work in all the different cloud providers for different customer use cases.
With that in mind, what were some of those challenges when you initially started, like, all right, I'm going to put Pulsar on Kubernetes? What year were we talking about? What resource did you have access to? What was that process like?
Yeah, so this was early 2019. I started looking at that. So the open source project, the Pulsar open source project, had sort of a series of Helm Charts, Helm Chart that had some of this stuff figured out. So I sort of started with that as my starting point. And it's like, I needed to get this running in the different cloud providers. And so because I'm going to provide a SaaS, Pulsar is multi-tenant. So I wanted to be able to provide a tenant level access to multiple customers from the various cloud providers. So the first I started from the Helm chart that the project provided, and then I ended up making my own version of that had a lot of extra features and functionality in it that we needed to get working. When we talk about data, the first challenge you always have to deal with is how do you deal with storage, and across the different cloud providers. That's one of the primary differences between AWS, Azure, and GCP is, what does the storage look like? How does the storage work? What kind of performance characteristics do you get on the storage? What you want to do there. And so, we primarily went with, shared disks or EBS volumes, and found that we could make a compelling, performance and cost trade-off there. And also reliability. I think, there's a huge reliability aspect to using, shared volumes or as opposed to local disks on say worker nodes.
Mm-hmm. Now, you touched briefly as well, and I'm sure you'll maybe get to this a little bit later once we start checking out your deck, but
yep.
The capabilities that, some of the things that Pulsar might offer that maybe some folks aren't aware of as opposed to Kafka, because as I mentioned before we got started,
yep.
we have had a few talks about Kafka. We've talked about Kafka, streaming previously, in the last 10 years, hearing about Kafka's the added value to big data. And curiously enough as well too, perhaps you can give a little bit of background about the naming of your previous company, because that has something to do with Kafka as well.
Yes,
so anyway, so just enlighten us a little bit about that before we get into the presentation.
Sure. So I mean, some of the like Pulsar came out of Yahoo 5 years or so after Kafka. So the original creators of Pulsar certainly knew what Kafka was, and they had evaluated it for their particular needs. And they were trying to build an internet scale messaging backbone for the use, for the use of Yahoo to support a number of services like Yahoo Mail, Yahoo Finance, those kind of things. And so they had a number of requirements around that. And they, at the time, and this is like, several years ago now, 2016, Kafka didn't quite meet all the needs that they had. One of the things they wanted to do is not only did they want to do streaming, where we have a continuous stream of data at high volume, they also need to do sort of your traditional queuing type use cases, where I'm going to put a message in a queue, I'm going to extract that one message, I'm going to consume it, we're going to do some work, and then we're going to ACK it. Those kind of use cases are actually not that easy to do in Kafka because it's built for high volume, high performance. Not, we have, in my company, we dealt with several customers that have use cases where I'm going to put a job into the queue. I'm going to then pick it up with a machine learning algorithm and process that for 2 hours, and then I'm going to acknowledge the message. Sounds like a pretty simple use case. It's actually not that easy to do in Kafka because it's not built for that. There's a lot of other, there's other performance advantages if you need to do low latency, low consistent latency was one of the other motivating factors. And I'll talk about it later, sort of how the Pulsar project leverages Apache Bookkeeper project for a distributed storage layer that gives it improved latency and read-write separation when you use that, as opposed to Kafka, which writes to the broker's local disk or the mounted disk. It has Pulsar separates compute from storage, which is often a useful paradigm when you're operating in Kubernetes or a cloud native type setup. If you separate compute from storage, you have a lot more flexibility in what you're doing. And Pulsar architecture, which I'll talk about later, definitely does that. So that's one of the key advantages. The architecture of Pulsar, that separation of compute and storage, the additional use cases that you can run on Pulsar are some of the key features why people are, I see more and more people are adopting or considering Pulsar for their messaging and streaming needs.
Well, that's a pretty good setup. Let's jump into the presentation. Let's get the show on the road. Let's take a
Sure.
look. Yeah.
Okay. I'll just share my screen.
All right.
Which is always challenging. There we go.
I know. That's what I said. Pulsar on Kubernetes is one thing. Sharing a screen on Zoom is totally different.
Yeah, that's the two different types of challenges, right?
All right. Cool. Gotcha now.
All right. Let me, now I can get to the window. Okay. Quick agenda here. I won't go over this. We've been so let's start with the backstory. I touched a bit on this when Bart and I were talking. I worked for 12 years for a proprietary messaging streaming company. One of the last things I did when I was there was I built a SaaS version of their messaging software. So I had some experience in what a streaming messaging SaaS looked like, and it's something that I wanted to build myself. So in early 2019, I quit my job and I built a company. I started a company called, which is still called Kesque technically. Original name for the company was Kafkaesque, sort of as a an ode to Kafka. It's like Kafka but different. And that name, as you can see, we've changed it over time. Some people loved it and some people hated it, which is sometimes a good thing for marketing. To also be controversial or and have that little bit of hate. It drives interest. But over time,
it's easy to remember and hard to forget. I think
exactly. Yeah. So we ended up shortening it to just Kesque, remove some of the letters in there for just, it was also the other downside to it. It was creating some confusion about whether we offered Kafka when we actually offered Pulsar. So anyway, we set out to build this company, and I wanted to build this business where we provide a SaaS, as I mentioned earlier, powered by Apache Pulsar. And as I mentioned earlier as well, my bet was on Kubernetes. I used Kubernetes. I'd seen the power of Kubernetes. So what I wanted to do is I said, everything we're going to do is going to be based on Kubernetes. The control plane aspect of, how you when a user comes in and they sign up, and how we configure them on the Pulsar clusters and all that, the control plane part, this was pretty easy. We did this also and based on Kubernetes, and we built a continuous delivery pipeline using GitLab. Which has nice tooling for this to actually automatically deploy your application to your Kubernetes cluster. The data plane part, the Apache Pulsar part, we were also going to run in Kubernetes on the cloud providers. We wanted to touch in regions around the world so everyone could have access, and also on all the three major cloud providers. As I mentioned earlier, at the time when I started, there was only some simple Helm charts part of the project, and that became the basis for Helm charts that we still use today. As I go through the history here, at what we used at Kesque, and now we use at DataStax for deploying Pulsar in cloud and on premise for different customers. So my main challenge, the control plane part, the stateless part's easy. How do I get Pulsar to run on Kubernetes and have it run reliably? So just backing up a little bit, what is Apache Pulsar for people that might not know about it? It originated from Yahoo. It was a project inside of Yahoo. It was donated to the Apache Software Foundation in 2016. It's a horizontally scalable distributed system, similar to Kafka. There's a lot of similarities if you're familiar with Kafka. It depends on Apache Zookeeper for metadata store, configuration management, leadership election, those kind of things. Pulsar are exactly the same as Kafka in that way. There's a broker, a Pulsar broker, similar to a Kafka broker, but Pulsar has an additional layer, as I mentioned earlier, for storage provided by Apache Bookkeeper, which is a separate project that's used in various different other projects as a base. It's a distributed log, a distributed storage kind of project, which I'll talk more about later. Pulsar, every message that or event or whatever you want to call it that you send to Pulsar, and this is different than Kafka actually. Every message you send to it is persisted to disk before it's acknowledged back to the producer. In Kafka, what happens is periodically messages are persisted to disk, and it's a configurable amount, and you can get it to happen very frequently and per message, but by default, Kafka will only persist messages to disk on a periodic basis. What this means is that in a failure scenario, you can lose messages on a particular node. Of course, there's replication factors to sort of compensate for that. But one thing with Pulsar, because it persists to disk, we can lose it. We can lose a data center, or we can lose an AZ, and the last message that was acknowledged, we can be sure that's actually on the disk. Like Kafka, Pulsar has been built for and works well in high throughput, low latency use cases. There's some benchmarks out there, and I ran some myself just to get a feel for this. One thing if you run these benchmarks, you can see Pulsar's latency is consistent because it always does the same thing. It sends the message, it flushes it to disk. The path is always the same. The latency you get is consistent over time. Kafka, you'll see like spikes in latency depending on what it's doing at different times. Pulsar combines, streaming capabilities where you can send messages very quickly, like click streams, for example. You can collect all of those, aggregate them. You can do pub sub, where you're going to publish a message and you're going to have multiple subscribers, and you're going to fan that message out to multiple subscribers. And as I was talking about earlier, it can also do queuing patterns. These are kind of traditional patterns. Think, maybe SQS, simple queuing patterns. Doing those at high speed and with high scalability, you can do that in Pulsar as well. These things are challenging to do in Kafka. It has a long list of built-in functionality, has built-in multi-tenancy, has built-in geo-replication for disaster recovery or for worldwide distribution, has a built-in schema registry. It can do something called tiered storage, where we offload messages. to S3 or some other blob store to reduce costs, which is important. And it can also, you can build functions that streaming functions that will operate per message. This whole framework is built right into the Pulsar project. You can do a lot of this stuff, with Kafka. Multi-tenancy is really, really hard to do in Kafka. But a lot of this other stuff you can do, but it's separate projects. It's separate, sometimes commercial products. You have to kind of cobble it all together. With Pulsar, all comes in one project, one container. So that's a bit of an overview of what is Pulsar.
Diving in sorry, Chris, but is this the part of the interview where I can put the link to the book that you wrote?
Sure. Yeah, I did. I wrote a book comparing a Pulsar and Kafka for a ride, an ebook. It's a short book. There's a lot more detail in there than what I just
no, but just, I think we're stimulating interest on this, so it's good so that people have a reference.
I don't have it handy, but I can get it for you unless you have it.
Okay. Excellent. Keep going. Fantastic.
Okay. Just a little bit more detail on the architecture of Pulsar, just so you can understand what we're doing when we run it in Kubernetes. As I mentioned, there's Zookeeper. You have to have multiple Zookeeper nodes for config and metadata storage. And then the broker layer, which is the compute layer, you can see producers and consumers only connect to the broker. And the broker handles all the movement of the messages. But the storage of the messages, right, because we're going to persist these messages, we want to make sure that we guarantee the delivery of at least once delivery of messages, which is what Pulsar does and Kafka and other kind of persistence messaging systems do. We're going to have to save that somewhere. We're going to have to put it on disk somewhere ultimately. And Pulsar uses this whole separate layer called Bookkeeper in this project. And the interesting thing about Bookkeeper is you can store a topic, that's the main construct that we use in Kafka and Pulsar. Is we have a topic, it has a bunch of messages, a bunch of events in it. In Kafka, those are all written to it. The broker itself has mounted disks. We write that to the broker disk. In Pulsar, what we do is we take the messages and we group them up into segments or ledgers in Bookkeeper terminology. And we're going to write those not to a single server, but we're going to distribute those across multiple servers called bookies in the Bookkeeper project. So this means that, like, for a single topic, no one server has the entire set of data that's associated with the topic. You get a lot of advantages with this because the failure of a single node doesn't mean that we lose an entire topic. We just lose a segment of it. And because we're doing replication, we're just losing one of the many copies that we have of a node. This makes a lot of failure scenarios and recovery scenarios much easier to handle in Bookkeeper. It also makes it easy for you to expand Bookkeeper. You can add more nodes, and it just starts adding those segments onto those new storage. There's no storage nodes. There's no need to move segments around or data around. No rebalancing. That kind of stuff doesn't have to happen. It's all sort of handled for you automatically. You can also stripe writes across multiple bookies. If you have a really large data volumes, you can have multiple bookies, and you can sort of take these segments. And we can, if we have a replication factor of 3, we can spread those 3 writes across 5, 6, 7, 8 bookies. So then we can get the advantage of the striping, the parallelism of that. So we can push a high volume of data into the Bookkeeper project as the base for Pulsar. Diving down a little bit in Bookie, and I often call Bookkeeper the secret sauce to Pulsar. On the Bookkeeper itself, there's actually 2 disks, or that's the recommended configuration. You have 2 disks. You have a journal disk and you have a ledgers disk. The journal disk is where all messages are written. They first are written to the journal disk, and they're F-synced. They're synced to the physical disk for every message that comes in. That's your write path. If you look at a journal disk and on a live system, you see that there's almost no reads going on the journal disk because it's just a write-ahead log to make sure that we have all the messages written persistently to storage so that we can recover from any failure scenario. At the same time as the message comes in and it's getting prepared and it's putting on the journal, we put it in memory, we reorganize a little bit, and then it gets written to the ledgers disk. And the ledgers disk is where it gets read from. So, separation of input and output. The journal disk is write only. The ledger's disk it has to be written to, of course, because we're going to write it there as well. But it's where the messages get stored for long-term storage, and any kind of reading that we need to do comes from the ledger disk. So the advantage of this is if you have high write throughput coming in to your bookie, and you have sort of an event where you have to do a lot of catch-up reads from a topic that's sort of maybe the consumer's been down for a couple hours, it doesn't impact the write because it's a separate path. So you can maintain performance under various sort of failure conditions in Pulsar because of this Bookkeeper architecture. And that's what I was talking about earlier, is like a lot of people look at Pulsar and they go, this is a really good architecture. There's a lot of advantages to the way it was built. And of course, the creators of Pulsar had the advantage of seeing what others had done in this space and kind of taking the best parts and making them better. They reused a lot of the functionality or the concepts, or they reused Bookkeeper, but the Pulsar team also made lots of contributions to Bookkeeper to get it to this level and to make it work really well with Pulsar. So when you look at it, one of the things that it really jumped out to me is like Pulsar running in Kubernetes, right? It's like, everyone knows, stateless applications, that's the way to go. That's, the first generation of Kubernetes applications are stateless. So the nice thing about Pulsar is part of it is stateless. It's not all stateful. The brokers themselves, right? As you can see in the diagram that I had prior, the brokers are stateless, and because they're stateless, we can scale them up and down arbitrarily, however we want, right? And when you scale them up or down, they can have different load on them. And Pulsar has a built-in load balancer, which continuously monitors the memory and the CPU and the network usage on the brokers, and it'll redistribute the topic load for you. So this is all automatic. You don't have to. There's no rebalancing and manual intervention required at all. So this means you can scale up and scale down. So it's really good this way. And as I mentioned before, we separate compute from storage. So depending on what your use case is, you may need a lot of compute, but not a lot of storage, right? If you're not actually storing the messages for long term, you just need to process the message and get it out quickly. I work with customers these days who have tens of thousands of messages per second. They produce that and they consume it almost immediately, except for in failure scenarios. So we don't need a whole lot of storage for those use cases. We may need a lot of brokers, because they have a lot of clients, a lot of connections and whatnot, but we don't need a whole lot of Bookkeeper storage capability. And so the advantage of Pulsar is you can kind of optimize the resource usage because of this. You can easily scale up brokers up and down as you want. Like I have the example here of the familiar kubectl scale command. That's as easy as it is to move the number of brokers in your Pulsar cluster up and down. And you can they say make that match your use case and make the storage layer, which is usually a very expensive part of your deployment, right? Disks are expensive, especially if you have them for the entire month, and they're large disks because they have good performance. They're not cheap, right? So if you can optimize the storage layer down to what your minimum set is, and you can scale out the serving layer, you have a much more interesting and much more cost-effective way of running your messaging system. Brokers are stateless. That's great. Obviously, we have to have stateful things happening here. Zookeeper, which is common with Kafka and lots of other projects, is obviously stateful. It runs as a stateful set when we run this in Kubernetes, backed by persistent volume claims, PVCs. And so Zookeeper is pretty standard. Lots of people have sort of got that running in Kubernetes. When we do Bookkeeper, which is something that's particular to Pulsar, we have to have two PVCs, one for the journal, one for the ledger disk. Those are typically different sized. The journal can be very small because the journal is really just a write-ahead log, so it keeps a small portion of the data. And once it's committed to the ledger's disk, we don't need it anymore. But we can scale both of those things. So we scale both the Bookkeeper and the Zookeeper horizontally. Up is easy, and usually down is sometimes not so easy. Zookeeper, as many people probably know, require an odd number of pods, 3, 5, or 7. which can sometimes be a challenge if you have an even number of availability zones in your cloud provider, and you're trying to account for failure scenarios. Bookkeeper, though, you can use any number of Bookkeeper nodes. You can use 1, 2, 3, 4, 5. It doesn't have to be an odd number. You can, but usually you start with at least 3 for a replication factor of 2. Then we can tolerate the failure of 1 of them. So one of the key challenges to running Pulsar in Kafka too, because they have the same behavior here in Kubernetes, is external access. Kubernetes is great if you want to do internal access. You have local DNS, you have local name resolution, you have local IP addresses, and that's great. If you're going to build a SaaS, you're not going to let people have access to your internal Kubernetes cluster. We have to provide external access so people can connect on public IP addresses to your service and use TLS and these kind of things, right? So that was a major challenge, is getting external access to Pulsar. And this is why, because in Pulsar, a topic is owned by a single broker. So if you have 3 brokers, one of those, and you're publishing or subscribing to or consuming from a topic, one of those brokers is going to own the topic, and you have to connect to the right one. And if you connect to the wrong one, that's not a real big problem if you have in the local case, because Pulsar will say, hey, this is the wrong one in this response. You do this. So the first protocol message is a lookup. Say, okay, I wanna publish or subscribe to this topic. And then Pulsar will respond and say, either yes, that's me, if you got lucky, or it'll respond, no, that's not me, go talk to this other broker. And every broker has the full knowledge of this. It's actually stored in Zookeeper. So every broker knows who owns all the topics at any time, right? But if you think about this model, what it requires is that every client needs to be able to talk directly to every single broker. And this is not, from an external access perspective, this is not a model that Kubernetes is very supportive of, right? For Kubernetes, your standard access model in a cloud Kubernetes installation would be, I would add a load balancer that would then, provide my external access, and then I would, to usually a set of stateless pods, round robin deliver those messages, those connections to those pods. You can't do that with Pulsar because the underlying broker pod that's running inside the Kubernetes cluster, the client would need to be able to talk to it, but that pod is running with a private IP address or a private DNS name from within the cluster. So this is a challenge, and one of the first things I had to sort of get my head wrapped around, and how do we deal with this in the SaaS? How are we going to make this work? And it's also a problem too for other customers that I have that we do deploys for them on their internal cloud. Or in their own cloud account. For the separation purposes, some people don't want to run their applications on the same Kubernetes cluster as Pulsar is running on. Also because we remotely access these things, so just for security reasons. So they have the same problem where they, how do we basically run Kubernetes cluster that is just Pulsar and have maybe our applications running on a different Kubernetes cluster, or maybe just running on VMs and things like that. So it's an important problem that we had to solve. The good news about that is the Pulsar team thought about this problem right from the very beginning. In fact, if you look, there's, like most open source projects, there's a bunch of improvement proposals that happen. People put out proposals, and then there's discussion, and then it gets implemented or it doesn't. The very first proposal, PIP, it's called Pulsar Improvement Proposal, was the Pulsar Proxy that was ever written. The Pulsar Proxy enables remote access to Pulsar through a proxy layer that is stateless, and this makes it very easy actually to expose Pulsar to use it in Kubernetes to external connections, any kind of external connections. And we use this use this in all our Kubernetes deployments of Pulsar pretty much, even if they have internal connections, because sometimes you want to have external access for debugging purposes. The Pulsar proxy understands the Pulsar proxy protocol enough so that when you connect to the proxy, it does the lookup and is able to understand, figure out which broker it should connect to. Now, the proxy runs inside the Kubernetes cluster, right? So it has access to all the local IP addresses, all the local DNS names, and then it can make the decision about which broker to ultimately connect to. And then it, after it does that sort of negotiation and figures out this is the broker that I should be talking to, then it just becomes a simple like reverse proxy, TCP proxy. So it handles this part. It sort of isolates the end client from having to know which broker they're talking to. The end client talks to the proxy exclusively. We can have multiple proxies because they're stateless. Pulsar proxies, they're stateless. You can connect to any one. So we put a load balancer in front of them. And as the new connections come in, it just picks one. And then that proxy will handle the forwarding of the traffic for the duration of the connection. The connection drops for whatever reason, it may go through a different proxy next time, but that's not a problem. So when we run Pulsar in Kubernetes, as I mentioned, there was Helm Charts available. We still use Helm today, in all our deployments for Pulsar. I personally think it fits well with sort of the paradigm of Helm, being able to upgrade and roll back. Personally, when I'm debugging things and trying to figure out stuff, the fact that I can, Helm generates manifests that are consistent and I know what they are, but I also can make temporary changes to the manifests directly, which is something in an operator world is hard to do. I think it's very powerful and I think it works really well. And there's not a lot, because Pulsar scales relatively easily. Brokers and proxies are stateless. They scale fabulously. And Zookeeper scales okay, up and down if you configure it properly. And so does Bookkeeper. So we're like on the verge of perfect fit for a Kubernetes application. It's very cloud native or Kubernetes native. So all we really need is something to manage the complexity of all the manifests, which is what Helm is great at. So that early Helm chart that we started with back from the open source project, as I mentioned, has gone through, and I didn't really talk about this, but in late 2020, Kesque, my company, was acquired by DataStax, and we've rolled all of that in, and now we have our DataStax version of the Pulsar Helm chart. This is a variation of this. This started as the same Helm chart that we use in production at Kesque. And we'll talk a little more about it later. At DataStax, we're building a new service, a new SaaS powered by Apache Pulsar, which is called Astra Streaming. All three of these things, the native Helm, not all two of these things, the Kesque service that still is running a little bit today, the new service that's coming out from DataStax, it all is built on the back of these Helm charts. And we've over time added quite a bit of functionality to the charts to make it easy to deploy and handle a bunch of functionality. It's an umbrella chart. It embeds the cert manager chart. It embeds the Kube Prometheus stack for us to get Prometheus and Grafana and alert manager, all of that in there. We run the entire monitoring stack and everything from the Helm chart when we deploy it, sort of one big package. As I talked about a little bit earlier, an operator, a lot of people would say, a lot of people ask me, is like, do you have an operator? Do you use an operator for Pulsar? Operator would be nice, but I think the main reason to have an operator is when you can't do things in a way that's native to Kubernetes or Helm. That's the native tooling. You need to shut something down in the process of scaling it up or down or doing an upgrade. And that none of that is necessary for Pulsar. So, I don't see a compelling reason to add an operator to Pulsar, to run Pulsar in Kubernetes, because you don't really need it. And there are things, like I mentioned before, where I find it's when the operator has control of the manifests, then you can't make small changes and do debugging and that kind of stuff, which is important for me anyway, as we're operators of Pulsar, and we get into complex situations that we have to look at.
Since you are talking about Helm, and earlier that we had this week we had a streaming live stream about different kinds of tools. And there was a
Yep.
brief discussion about Helm versus Customize. Have you ever tried working with Customize in Pulsar?
I have done a little bit of work with Customize. I still prefer Helm. It has more rich templating language. You can do a lot more. I find that, and I use Helm much more extensively, so I am biased. But the little bit of exposure I've had to Customize, I found that it's too simplistic. I can't do some of the things that I want to do with Customize. It generates manifests, but it doesn't have that rich programming. Or you can basically do anything you want in Helm through helper functions and things like that. So maybe I'm not enough user of Customize, but I find that Helm is much more flexible.
Fair enough. Awesome.
So just a little tour here of sort of what it looks like with Pulsar running. In this case, it's in the GCP cluster. We have a stateful set for the bookkeepers. Bookkeeper 1, 0, 1, and 2. Broker deployment. 3-node broker deployment here. We also sometimes run brokers as stateful sets, and the reason for that is not because they are stateful. It's because we need stable names for them. There's some features in Pulsar that, because Pulsar started as pre-Kubernetes, make some assumptions about having a fixed name for a particular broker. If you're not using those features, I prefer to use a deployment. If we are using those features, then we'll change, and the Helm chart supports this. We can change the broker to a stateful set deployment. It's almost the same. We don't mount any volumes. All we do is we have fixed names, brokers 0, 1, and 2 in this case. We have a proxy deployment, similarly, stateless proxy deployment, and we have a Zookeeper stateful set. For all of these things, when we run the Helm chart and we run in production, we use host anti-affinity rules in Kubernetes to ensure that none of these components run on the same node. And if we're doing multi-zone deployments, multi-AZ deployments in clouds, we will use zone anti-affinity. Especially, it's not as important if you have like one node per zone, because you pretty well reduces to the same thing. But if you have multiple nodes, you have 2, 3 nodes per zone. You don't want all your bookkeepers to sort of crowd up into one zone. So you will also use zone anti-affinity in those cases to make sure there's a nice even distribution of the bookkeepers across the different zones. One other thing that we do is in the Helm chart, and I found it's very, very powerful. When you start up Pulsar, there's kind of an order of operations. There's a bunch of dependencies here. And one of the things that I did when that wasn't supported in the original Helm charts, is something I added, was extensive use of init containers. Not to do a lot of initialization, but just to coordinate the bring up of the pods. Everything depends on Zookeeper. So there's really no sense in bringing up any of the other pods unless Zookeeper's up and running. And Bookkeeper depends on, the broker depends on Bookkeeper, and the proxy depends on the broker. There's this whole dependency chain. So what we've done is we use like simple scripts, inside an init container that will pull for various conditions to not bother starting a pod until its dependencies are started and running correctly. First we make if you do a Helm install of one of our Helm chart, you're going to see Zookeepers are going to come up first, and everything else is going to just be waiting in a init. Until Zookeeper is up, there's no sense in starting anything else. There's actually some initial configuration that needs to be done in Zookeeper, which gets applied by a job, and then once that job has been run, then Bookkeeper comes up. It waits for that Zookeeper config to be applied. The broker waits for the bookkeepers to be up, and the proxy waits for. So we do this to have nice orchestrated kind of bring up. Otherwise, what you get, in the past, where you'd have these, these dependency components would be just crashing, and they get into crash loop backoffs because it takes a little while, especially if you're provisioning volumes and things, which I'll talk about later. For these, it can take a while to bring up Zookeeper, and if you have a lot of bookkeepers, and then your brokers are in crash loops, it looks like a disaster, right? So we use init containers to sort of consistently bring up everything. It's also great, actually, I remember now the main driver for this was for unit testing, or like doing kind of testing, because if you go in a crash loop back off, then it's non-predictable how long it's going to take things to come up because it's in the back off state. So I wanted to have a nice orderly startup so that we can, within a fixed amount of time, be sure that either it came up or it didn't come up, and then we can run some tests after that. So that's, I think, important part and something to look at, I think, for not just stateful applications, but applications that have dependencies on other applications, or pods in this case. So as far as persistent volume claims, as I mentioned, we have stateful sets for Zookeeper and Bookkeeper. I'm mostly use cloud disks for the PVCs. If I whenever I can, I do. And the only reason not to use it is for performance reasons, or if I'm not in a cloud provider. The advantage, to me, the huge advantage of using cloud disks for PVCs is that they have their own life cycle. And so you can lose the node, but the disks persist after that. And then the disks themselves, and most cloud providers, have very high durability. So the odds of losing the data on those disks is quite low. And if you remember, Bookkeeper flushes data to the disks every time it does a write. So we have a really high probability or really low probability, extremely low probability of losing any data in these cases. And if you do have problems with your worker nodes and things, you just spin up a new worker node and you mount the disk, and away you go. If you have local volumes attached in your worker nodes, and sometimes we do this, obviously you have to deal with the failure of a node. You can also lose the disk contents, and then you have to re-replicate things and whatnot. Unless you can't, I would always recommend using cloud disks, or if you're on premise, some kind of a project that delivers this kind of capability where you can provision a volume dynamically, and you can it has its own life cycle independent of the worker node. As I mentioned before, there's two different disks on the Bookkeeper. You can see we generate a journal disk for the Bookkeeper, and I think I said this before. It can be pretty small. We can 25, 50 gigabyte is usually enough for that. The reason why you might not want to go quite that low, even though you can, is that it's changing now with some of the GP3 volumes in AWS and in some of the other cloud providers, but typically those small disks don't have very good performance parameters. So you want to maybe make it a little bit bigger to get the higher performance, because the journal has heavy writes. So you do want to have a fairly performant disk there, but you don't have a lot of storage requirements. And then the ledger disk would be the one that we would, be a large size. An example setup would be, a 250 gig journal disk and a 4 terabyte ledger disk, which would give us a big storage requirement, a big storage capability there. And then Zookeeper disks need to be, don't need to be terribly large, because everything in Zookeeper memory is also on disk, and there's some snapshots, so there's a little bit of amplification there, but you can get with sort of smallish size disks too with Zookeeper. Compared to Kafka, and you hear a lot of horror stories about Zookeeper and Kafka. I mean, the usage of Pulsar's usage of Zookeeper is minimal, so it's not constantly connecting and getting data from Zookeeper. So the load it puts on Zookeeper is relatively small. So you don't need monstrous Zookeeper setups to back a Pulsar cluster. And if there's there's a couple things you want to tune probably on disk volumes. I'll just leave them here. Just that we found that we do a little bit of tuning on the brokers and the bookkeepers for these volumes, because there's extra latency and whatnot as opposed to a locally mounted disk, but we can get good performance out of these. One thing that we use a lot and we rely on, and especially cloud providers when we're running Kubernetes, and it's a great feature, is volume expansion. I can't tell you how many times volume expansion has gotten me out of trouble. often you may get to the point where your bookkeeper, and again, this is a separation of compute and storage. Your bookkeeper node may have plenty of CPU and memory to handle the load, but for whatever reason, storage requirements have increased, and now it won't fit the data that you want to store. It won't fit on the disk anymore. Yes, I could spin up a new bookkeeper, but that's kind of expensive, especially if I don't need the compute and storage. So we take advantage of the ability to resize persistent volumes in all the major cloud providers. And as I mentioned, the ledger is where we stored most of the data. So that's the one we always end up expanding. The journals, we don't ever have to expand those. So I would, these are kind of things, if you're setting up Pulsar to run, I would recommend on your storage class to make sure that you set volume expansion, because that needs to be enabled. It hasn't always been, I don't know, I don't think it's a default. I certainly hasn't been the default, and maybe the default now, but it hasn't always been so the default. So you want to allow volume expansion to be true. And then if you're in a multiple AZ zone, AZ kind of setup, you want to make sure that you're using wait for first consumer as well in your storage class. Otherwise, what will happen, and we've seen this happen a lot, is before we started using this consistently, is your pod and your PVC will get in parallel created. And what will happen is your pod is created in one zone and your PVC is created, your PV is created in a different zone. And now they can't mount each other, because in most cloud providers, you can't cross mount persistent volumes across zones. By using the wait for first consumer, the pod gets scheduled first onto a particular node in a particular zone. Then we create the underlying PV, so we don't have this problem of mismatching between zones. If you don't do that, you end up getting into this kind of a state where you have to keep recreating pods to try to get them to match, get scheduled onto the zone that you know where that you know has the volume on it. You can avoid all of that kind of complication just by using wait for first consumer. One caveat on this, when you're running in Azure and you need to resize the PVC, it does work. It's just really complicated. It doesn't happen automatically like it does in the other cloud providers. So you have to do this complicated procedure of coordinating all the nodes, restarting pods. You have to make sure that the volume is not mounted. It can't be resized while it is mounted. And the other cloud providers, they don't do it while it's mounted, but you just have to restart the pod. In Azure, you have to hold the pod unmounted, the volume unmounted for a long time, so it can do the resizing, which has this complicated procedure that you have to go through. One other thing to note is if you do volume resizing, now and you're using Helm, right? Your stateful set will be specifying the size of your persistent volumes. So if you scale out a new one, it's going to use the old size, right? Say we went from 1 terabyte to 2 terabyte. Now we scale out all our Bookkeeper PVCs. We expanded them to 2 terabytes, and now we spin up another Bookkeeper. Now that one is only going to be 1 terabyte if you don't do anything else. There's a way around this. You can, basically you can delete your stateful set. It's a bit treacherous to do, but you delete it without cascading the deletes, so the pods for the Bookkeeper keep running. Then you can update your Helm configuration and do an upgrade. So now your Helm generated manifest match what you want with the larger size. So that's something that that we've done a few times and been caught with that not set correctly, and then having to resize volumes after just spinning them up. It's a bit of a pain. Tiered storage is another great feature of Pulsar that we use on a lot of our deployments. It's not Kubernetes specific, but it is an interesting feature, so I thought I'd just throw it in here. Obviously, SSDs SSDs are expensive, and you need them for fast access. But as data, if you're storing data in topics, and the older it gets, the less important it is, and the less you need to get a fast retrieval of it. So what Pulsar lets you do is configure tiered storage, and that will then say past a certain amount of time or a certain amount of size, we're going to take messages that have been stored in a topic, and we're going to take them off of these fast, expensive SSDs or cloud volumes, and we're going to push them into blob storage, lower cost blob storage like S3 or Google Cloud Storage. This can significantly reduce the amount of the size of the SSDs that you need to maintain, to as long as you don't need to retrieve those super quickly. Obviously, it's going to be slower to retrieve those messages from S3 than it is from a SSD. But if you've waited 2 days to get the message, the fact that it takes a few hundred extra milliseconds to get it probably doesn't matter. And this is all completely transparent to the client as a user of Pulsar, the client user of Pulsar. There's no flags or anything. It just happens transparently. The messages get pushed off, and then when you to the tiered storage, and then when you go to retrieve them, they get delivered to the client. They get pulled into the broker, and then the broker sends them to the client. It's completely transparent. This means Pulsar lets you do things like event sourcing, where the architecture where you would store all events in your messaging layer. And all events can take a lot of space after a while. So we have users who will do event sourcing type use cases, and they push the old events off into S3 to reduce costs. As I mentioned, it's a lot cheaper, and also there's usually like tiering in S3. So you can say, well, after a month, I want to move this to a different class of blob storage that's even cheaper, as long as you can accept the delays in retrieval. Running low on time here. I want to leave a little bit of time for questions if there are at the end. We use Liveness Probes extensively. Find this is very helpful, and especially when early days of Pulsar. Go back 2 years, there were some stability issues, robustness issues. This saved my bacon a few times by having these probes restarting pods or when they're unhealthy. So a little idea about node pools when running Pulsar. For a small cluster, we will often run a single node pool. We'll run all the Pulsar components in a single node pool on 6 nodes. I like to use 6 nodes in a standard Kubernetes cloud deployment. That'll give you 2 nodes per availability zone. I think this gives you really nice redundancy in the event of a failure of a zone or a failure of a node in the zone. So we will do that, and using EBS type volumes. This works really well for a small cluster. You can get a really for not a lot of cost, a highly functioning and fairly performant Pulsar distribution or Pulsar setup. For a medium-sized cluster, what we often do is split it. We'll create 2 node pools. Bookkeeper with the disks and is the most sensitive one for performance. So we'll create a separate node pool for Bookkeeper and run the Bookkeeper nodes pods on those nodes, and then we'd have another node pool for everything else. And then if you're getting to a really large deployment, that's when we start breaking out node pools for each major component. A node pool for the zookeepers, a node pool for the bookkeepers, a node pool for the brokers, and then maybe a node pool for everything else, the proxies and some of the utilities that we use. And in this chart here has some ideas on sort of kind of the sizing, some sample sizing from some production clusters that we manage to give you an idea. So the Bookkeeper is the most memory intensive part of the setup. Bookkeeper, broker, then proxy if you're running this. Upgrades. When we do upgrades, one of the key things that we do for Pulsar is we upgrade each component independently. We do handle this in the, you can see here in the Helm chart, we have individual tags for each component, which is a little bit different than a lot of Helm things where you have like one tag for all components or the whole chart. We broke it up into multiple ones so we can do sort of a staged upgrade, especially for production, high volume production environments. We'll upgrade Zookeeper, then make sure everything's all right. Upgrade Bookkeeper, make sure everything's all right. Upgrade the broker, those kind of sort of step by step, in a careful way. Talk about just a few of the tools, just in case people are interested in what we use a lot. We have something called a Bastion pod, which is a pod that runs inside the cluster. This thing is really, really useful. We start that up and we pre-configure it to be able to connect to everything and a bunch of tools on it. a very, very useful thing for debugging. I recommend, if you have any kind of large scale deployments, to have something that, you can forward into, and run commands and sort of judge the sanity of your deployment. Kubetail, which just tails multiple logs. You see we have multiple pods for everything. That's very common. One plugin we use in Helm a lot is the Helm diff plugin. This was key for us as we have multiple people working in the same environment, making updates or trying changes and things. Without the Helm diff plugin, we were sort of trampling each other all the time. At least so the Helm diff plugin just compares the manifests that you're generating to the ones that are there and shows any differences. And so, when we do a change, you look at the differences, say, is this the set of changes that I expect? And if there's any unexpected changes in there, you're like, well, maybe somebody else has changed something. That's the time to get on Slack. It's like, hey, who changed this or what's going on? So we use that all the time. Before we started using it, and we started saying, thou shalt use Helm diff before you do any kind of Helm change, we had lots of problems. And K9s is a go-to tool. We use that all the time for managing the cluster. And the node shell plugin for kube control, which allows you to shell directly into the worker nodes, is also helpful. We don't typically expose the worker nodes, so we use that to log into them. It's been especially useful recently as we've moved to rootless containers in our Pulsar distribution. So we don't have the access to install things ad hoc in any of the containers. Sometimes you have to go into the worker node and run some commands that you can't do otherwise. Just to complete the circle, I already mentioned this. In late 2020, Kesque was acquired by DataStax. DataStax has a history of supporting Kubernetes and doing a lot of Kubernetes work. One of the a couple of the things that you may have heard of is the CAS operator. So it's operator for Cassandra. There's also Kate Sandra, which is it includes the CAS operator. It's like a full-blown setup with all the parts you need. It's a lot like our Pulsar Helm Chart, actually, where it includes monitoring and other tools, useful tools in the package. Those are a couple of projects. And when we were talking about whether should we join DataStax or whatnot, the fact that DataStax is obviously behind Kubernetes and is building projects on it, to me was a perfect fit. We have the same kind of strategic vision of where things are going and how we should build. And so that's what we've been doing. Since we've been part of DataStax, we've released Luna Streaming, which is Apache Pulsar distribution with a Kubernetes first kind of approach. Is like people want to use Pulsar in Kubernetes, and that's our primary way of delivering it to them. And as I mentioned earlier, we're working on Astra Streaming. It's in beta right now. Is our SaaS version of Pulsar that's built on Kubernetes, and it's also integrated with the DataStax Astra DB product, which is Cassandra as a service. So you can do Cassandra and Pulsar in the same service. All of this is built on Kubernetes, and there's more things that that you'll hear down the road coming from DataStax in the Kubernetes space. Just leave it here. If anyone wants to check out some more information on Pulsar itself, there's a Slack channel for Pulsar. You can sign up and talk to the community, very welcoming, and some information on Luna Streaming and Astra Streaming. That's it for me.
Good stuff. Very, very complete, very well-rounded. We can tell that you have written a book about Pulsar. This is abundantly clear. If there were any doubts beforehand, it's not just writing a book. It's not just, you can walk the walk and not just talk the talk. Having said that, all right, yep. You gave a very thorough overview of Pulsar, and also looking at, the differences in capabilities with Kafka. If you could improve one capability or feature of Pulsar, what would it be?
Improve one feature or capability?
Yeah.
That is an excellent question.
You don't have to answer now.
No, sorry.
Let
me think about that.
No, because we've had other speakers that get really deep on a specific tool or a specific database or things of that nature. And I always find it interesting to think about, okay, like if we're at here right now, what's the next level? It's really, really good, but if you just get into this one thing a little bit better, what would that be? That's okay. But that's
now I've come up with it now.
Okay, cool.
Well, one of the things, one of the things, especially is, I talked about tiered storage, right? And I think that's a powerful way to save money and do things and right now, when you write to disk, it also, it writes to that ledger disk. I think if we were to, one improvement we could do that would even make it even less expensive is that, we still have that journal disk to capture the message, make sure we have that message for any kind of failure scenario. But if we could write that directly to S3 right away and sort of cut the ledger disk out, we could significantly cut the costs. Now, whether we could get the performance we want or not, but I think that would be sort of for cloud native kind of Kubernetes deployments where you have an S3 compatible access either on premise or that. I think that could be a nice way to even reduce the cost and make it easier to run and it also facilitates, I didn't even talk that much about geo-replication, is like the advantage of having something in a cloud provider like S3 or even we did a little bit of partnership with Storage, which has their own sort of global, S3 compatible storage network. You can kind of now, if you switch to another region, you can still access the data because it's in this global system. It's not local anymore. So I think there's some interesting things we could do there to make Pulsar even more friendly and work even better in a cloud environment.
That's particularly that's particularly exciting as well too. Thinking as we live in more and more of a global, society, we have to be taking those things into consideration as we have, where remote work is expanding and being able to have that access regardless of where you are in the world. That's a good point to keep in mind. Other stuff to keep in mind, because you also mentioned, and particularly attacking that issue of cost, I find that interesting too, because with storage, it's no secret that these things can get quite overwhelming quite quickly. And with that as well too, before we started the live stream, we were talking a little bit about when talking about Kubernetes, and once again, you being the person that was going out and directly talking to, has experience going out and directly talking to end users and say, great, this technology might do a lot of stuff, but what are the costs going to be here? And how can it be prepared for that? And that's also why we've had live streams with folks from KubeCost that are just specifically focused on, how can we keep these things under control? But what I wanted to get at is, we do have the financial cost issue. Then we also have the talent cost, right? That, right. How can, and so this is what I want to hear your thoughts on, is that it's the biggest challenge with Kubernetes, with writing data on Kubernetes right now, stateful workloads, databases, streaming, all these different things. Is the challenge a financial one? Is it a talent gap where there needs to be better specific training? We talked about this also with a couple of folks from Cockroach that were talking about certification. Should there be some kind of a data on Kubernetes certification? How would you go about doing that? Would that make sense? In your opinion, as someone who's been working on this quite intensively for a while, how do you see that? And what are the next steps that you think need to happen in order for this to become easier for organizations to see, to understand, and to start doing themselves?
Yeah, I think there's definitely, you mentioned this, there's sort of a knowledge gap there, right? We struggle with, one of the challenges of, as I mentioned, our Pulsar distribution is Kubernetes first, right? So you're going to use it, and most people will try it and they'll try to deploy it on Kubernetes. And the challenge we have is that a lot of people don't have enough Kubernetes knowledge, so that we end up having to try to train them to use Kubernetes before they can even get to our product. Or to run something they don't understand, sort of the basic stuff that will fail for you is like, well, if you don't have any access to any disks, then you can't deploy this on Kubernetes. You don't have enough memory, you don't have enough CPU. What does a pending state mean? The number of people have come is like, well, my pod's in pending state, and then they're like, I don't know what to do. Well, it's sort of basic Kubernetes stuff that you need to understand. So I think there is some level of like a certification or some training or some, I think that would be really helpful. It's like, these are the standard things that we need to do. These are stateful sets. These are how they work. These are the kind of considerations you have to have when you're using those kind of things. So that'd be helpful to make it more accessible to people. Kubernetes itself over time, they add features that make some of this, like volume expansion. I talked about that. That's a great feature. That's native, and I think it makes it more approachable, but you still need to understand what that is, and it's very, very deep technical. You can't use that feature unless you kind of understand how it works. And maybe I went into too much detail in my talk, but
no, not at all. I think that's generally I think it's a good problem to have to get everything on the table so that no rock is left unturned. Because in the same way that companies have maybe, and I saw this in a previous company where I was working, companies sprinting into the cloud thinking like, oh, I just download and that's it, right? Like, and then we just start rolling with it, and then you get these exorbitant cloud bills. Oh, why am I being charged so much? Well, because you have cloud tech, but you don't have a cloud culture. And so with Kubernetes, I think those are also similar questions that are going to come into play.
Absolutely. And I think too is also on the training side, as we're growing, we're adding new people, and some people come with limited Kubernetes knowledge, and having run something on your laptop a couple times, it seems easy, but when you sort of dive into the next level of detail, there's a lot of things that could go wrong, and that you need to sort of be aware of to run a more sophisticated kind of application on top of Kubernetes. Everyone can run a stateless set of Nginx, right? It's when you're doing more complicated things that extra knowledge and skill come into play.
Yep, completely agree. Anyway, Chris, that's all the time we have for today. But thank you very much. I do have to ask one final question though.
Sure.
We did have a battle royale once where someone compared. I
think I know where this is going.
A little bit of foreboding when you use the word battle royale, but it was his decision. Our great community member Tim Vandekeer, he addressed Argo versus Airflow, and looking at in his experience, data ops, applying both these technologies. And once again, it's one person's perspective. We're if it could be possible to get some of the Kafka folks that we've had, and to be able to have a very civil calm dialogue as much as possible, would that be something that you could find interesting? Be as someone who wrote a book about this.
Sure, I'd be happy to have that discussion. I think it's healthy, right, to talk about these things, and Pulsar owes a lot of debt, to Kafka. So I have great respect for the project and the community and that. But that doesn't mean we can't do things better, right? So we should always be trying to improve in both sides, right?
Absolutely. Well, we will have to hang on to that as a future date. But in the meantime, thank you very much. A very, very complete presentation. And once again, for folks that maybe joined a little bit late, we linked Chris's book in there. We'll have the slides as well too for people that got here a little bit late. Talk's obviously going to be on YouTube. Thank you very much, Chris. Looking forward to talking to you soon.
You're welcome.